what we need to talk about is next the trig functions. Derivatives of the trig functions. Gave you a little preview last time, didn't I? What did we do? We said the derivative of the sine was the cosine. Well, wanted to explain that a little more. They prove it out, nice and neatly in the book, but I wanted to approach it, the derivatives of the trig functions, via the graphs. Let's talk about, let's just start with sine. Sine of x, I'm sure you all remember what the graph of sine of x looks like. It's one of the wavy up and down curves, right? Starts at, it goes through 0, 0. Let's just say it that way. Right, it just bounces up and down, cycles up and down between -1 and +1. And it's got a period of 2 pi. That'd be 4 pi. It'd be minus 2 pi. Anyway, stuff like that. But from our viewpoint here, can't we sort of estimate the derivatives here? Graph the derivative function for the sine of x here. So if I was just going to graph the derivative off of this, remember where we started? We started with those horizontal tangents, didn't we? We've got a horizontal tangent here, 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 which winds up being over there 0, okay, right on the x-axis for the derivative graph, and you know this is pi over 2, right? 3 pi over 2. All right, so here's pi, 2 pi, so it's pi over 2 and 3 pi over 2 and minus pi over 2 and negative 3 pi over 2. Yeah. We do have zeros derivatives, so that's on the x-axis of the derivative graph. Okay? Now, if I go, say, well, let's just say I go from this peak to this peak, you see there, what's the derivative between this peak and that peak, or valley and that peak? What's the derivatives of the sine right here? What? Positive or negative? Well, the tangent lines are positive, aren't they? So that means the derivative over there, when we graph it, is positive. And notice it starts at 0 here, and then it progressively gets bigger, get bigger. I didn't do such a good curve there, but small positive, then it gets a little bigger and a little bigger. And then, of course, eventually it turns around and moves around. Okay? Not so good. Should have peaked right there at the axis. Draw that a little better. Okay? With me there? Then, when I go from this peak to this peak, or from this 0 to that 0, aren't we talking negative slopes? So negative derivatives, so below the x-axis over here. Yeah. And then it starts small negative, gets a little bigger, and then it turns around and goes back smaller. Okay, and then from, well, I didn't go to the next peak, but from this peak to this peak, we're back to positive. Then we're negative, and then positive, and then negative. Okay, and then from negative pi over 2 to 3 pi over 2, yeah, that's negative slopes. Yeah, it's doing the same thing back here. Okay. Well, lo and behold, what have I got here? It is cosine, isn't it? Cosine, well, we start here at 1, and then it cycles. You go, do have a period of 2 pi. It goes through one cycle there, like cosine does. Yeah, that is exactly the cosine curve. And like I said, they do more of a formal proof in the book, if you like to look at that. But from what we've done, the way we've approached this is pretty good. This is the cosine. So it turns out sine is your function, the derivative, comes out cosine. Now, it'd be really nice if it was vice versa, wouldn't it? Now, let's look at it. Let's start with the cosine. Which, yeah, starts at 1, at 0 anyway, and then just like we've got over there. Well, unfortunately, it is not just sine. I'll tell you that much. But let's look at it. All right, so here, this is pi over 2, pi, 3 pi over 2, 2 pi, so forth and so on. Okay, so here's pi, here's 2 pi. Where are the horizontal tangents for the cosine? Got a horizontal tangent at 0. Got a horizontal tangent at pi and 2 pi. And then minus pi and minus 2 pi. Yeah, at the pi's. So that means on a derivative graph, you got x-intercepts there. Which is looking pretty good because that's where sine has them. But, unfortunately, notice this. Between 0 and pi, what are the slopes over here of the cosine? Between 0 and pi, what are the slopes? They're negative, aren't they? They're negative. The slopes are negative for cosine between 0 and pi. Therefore, the derivative of cosine between 0 and pi is negative. So it does that. And then between pi and 2 pi, the slopes are positive. Negative, positive. So you see it cycles this way. They're positive from 0 to minus pi. Then from minus pi over 2, minus pi to minus 2 pi, they are negative. All right, so this is what we get. Is that sine? Here's sine. Is that exact match? No, it is not. Because sine goes 0, it goes up, then down, then up. However, how is that? It's very much related to sine, isn't it? It's just flipped over sine, minus sine. Yeah, the derivative of derivative of cosine is minus sine. Turns out it's not sine, but it's minus sine. So it's pretty nice. The derivative of sine is cosine. The derivative of cosine is minus the sine, as far as the trig functions of those go. Okay? All right. Now let's go ahead and do tangent. Just nothing else that reviews our tangent, our graphs of trig functions. What about the tangent? Well, tangents, those kind of little curvy things. Then we have the asymptotes. Remember that? Well, here's the thing on the tangent. If you want to think about here the derivative graph, approaching it that way, and I'll show you another way too. But think about the graph here. The derivative being the slope of the tangent lines. I don't have any horizontal tangents, do I? Because I don't have any peaks or valleys, so there's no zeros on this graph here. There's no zeros on the graph of the derivative. What else can we note here? Well, look at each one of these little branches. If you take a tangent line here, you got a positive slope. So the derivative is positive. If I take it here, I've also got a positive slope. If I take it here, positive slope, positive slope. Do I ever get a negative slope on tangent? Do not. There's never a negative derivative. So there's nothing as far as it goes there. But here's what we can say. It kind of starts, I mean, if you go out further here, it gets steep, and then it kind of levels out in sort of here, and then it starts getting bigger again. Here's what that translates to, which, by the way, this is 0, this is pi, this is 2 pi, right? Well, it turns out you've got those breaks also in, pi over 2, I'm sorry. These are at pi over 2. These are at pi's. Sorry about that. So at the pi over 2's, we've got a break in the graph, so that does, you don't have a derivative either, so you do have these vertical dotted lines in there at the pi over 2's. Just put the pi's and those in the middle. Okay, so anyway, what I was saying is, yeah, the slopes here, large positive, and they get ever so slightly smaller positive. So here's what that comes to mean. Each one of these branches, you start kind of big positive, and then eventually comes down, and then comes back around. Gets bigger and bigger positive. That's what happens. Big positives, slightly less, less, big, bigger. Okay. So each one of these branches looks like this. So anyway, you wind up with this, which looks a whole lot like secant. However, secant, remember secant, it alternates up, down, up, down, up, down, these things. This is secant squared. The derivative of tangent turns out to be the secant squared. It's never, derivative of tangent is never a negative. It's always positive. Those should be nice and level there. Sorry about that. Okay. So anyway, I was going to show you the other approach to finding this derivative of tangent. As you know, should always remember, and they're in the front of the book, on most of the books anyway, if they're not torn out, the reference page. As you know, tangent can be written in terms of sine and cosine. How can I write tangent in terms of my sine and cosine? It's sine over cosine, okay? Sine over cosine. Well, if I approach this then, knowing the derivative of sine, derivative of cosine, if I approach this as, well, use the quotient rule on that to find the derivative of tangent, you should be able to do that. Low d high minus high d low thing. Okay, so it's low cosine times d of the high. What's the derivative of sine? Cosine. Minus high sine of x times the derivative of low. What's the derivative of cosine? We just said that. Negative sine over low square. Well, look at that. Cosine of x times cosine of x is cosine squared of x. Minus sine times minus sine is positive sine squared x over cosine squared of x, low squared. Well, what do you know about this guy right here? Cosine squared plus sine squared. That's always 1. Yeah, that's just 1. And here's the other thing. The other trig identity of note here is what is 1 over cosine equal to? I split up cosine squared x means cosine of x times cosine of x. What is 1 over cosine equivalent to trig identity? Isn't that secant of x? Secant of x equals the 1 over cosine, isn't it? So I've got 1 over cosine, another 1 over cosine, so I've got secant x times secant of x, which is secant squared of x. And so that's a better way of kind of seeing what this graph really amounts to there. Yeah, the derivative of tangent is going to be the secant squared. All right, well, we could do similar things, but for the sake of time, here's the rest of the story. The way they arrange it, the table anyway, is they use the ddx notation, derivative with respect to x. So we saw that the ddx of sine of x, derivative of sine, is cosine. The ddx of the cosine, well, it was almost as nice, but it's minus the sine. And then we just saw the ddx of tangent of x is secant squared. So we'll need to know those. Like I said, similarly, we could go through the others, but here's matter of fact, we could do for the rest of these the ddx of cosecant. We could do very similar thing. Cosecant is 1 over sine. We could prove 1 over sine of x that this, what we get when we do the derivative on it. Well, it turns out it is minus cosecant cotangent. Cosecant of x cotangent of x. Like I said, it comes out, if you do this sort of thing with it, it comes out very similar. Use your quotient rule and all that. So that's the derivative of cosecant. It's minus cosecant cotangent. ddx, then let's do secant here. Well, it turns out the derivative of secant is secant x tangent of x. And then the ddx of cotangent, last but not least, trig function, is minus cosecant squared x. And there might be a couple in the homework where you actually prove those, like we did the tangent here. But a couple of points here. Of course, you can see some connections. Obviously, you got secant. The tangent, the derivative is secant squared. Well, cotangent, it's minus cosecant squared. So that's similar. And then, of course, these two have similarities: secant tangent, cosecant cotangent. And one note there is the derivative of cosecant actually has cosecant in it. Cosecant times cotangent, and the derivative of secant actually has secant in it, secant times tangent. And then, of course, these should be pointed out. We've got negative signs on several of these, half of them, matter of fact. But do you see when you get a negative sign for your derivative? What's the link there? It's the right? The co-trig functions. Anytime you have a co-trig function, cosine, cosecant, cotangent, the derivative is a negative. Whereas if it doesn't, you don't have a negative sign. So anyway, just a couple of notes because you do need to know those by